for this video, it would really be best if you had Desmos at a ready finger so you could do some work on it. The function I would like you to explore in this video is this one. I've drawn it up here, but it's the function f of x equals x cubed times e to the x. That's x cubed times e to the x. You might just hit pause here for a minute, get on Desmos, get a graph, see if you can get something to look sort of like that. Did you hit pause? Did you hit pause yet? Okay, I'm assuming you've graphed this, you have something like this on Desmos, and here's the question I would like you to explore. What do you think the derivative of this function in terms of a formula should look like? Now here's what a lot of people think. Now in the classroom, if you were here with me, I just asked you to throw out your best guess. And a lot of times people say this, because you've just learned some stuff in class about power rules and exponential rules, sometimes people say, oh, I get it. The derivative of x cubed would be 3x squared. And the derivative of e to the x we learned, so cool, the derivative of e to the x is just e to the x. And so sometimes people look at this and they say the derivative of x cubed is 3x squared, the derivative of e to the x is e to the x, therefore the derivative of this product of x cubed e to the x should be 3x squared times e to the x. Now, don't go back to Desmos yet, but suppose you did go back to Desmos and you graphed this derivative function. And you wanted to see if that derivative function made sense to you. But before you do it on Desmos, let's just think with our brains here for a minute. As you explore this function, do you see here that the derivative would be negative, and then the derivative right here would be 0, and then the derivative right here would be positive, and the derivative right in here looks to be back to about 0, and then the derivative is positive, and just keeps getting more and more positive as we go. So I would expect a derivative graph to show negative derivative, 0, positive, 0, positive. Let's see. So what I'm going to do, now you can join me in this. I'm going to go on Desmos and I'm going to graph what I predict is the derivative function. And there it is. So on my Desmos, in red is the original function, and in blue is our hypothetical, our conjectured derivative function. Now I hope you see that even right away there's some serious problems with this. I'm going to go over back to the board. I'm just going to do a rough sketch of this so-called derivative function. Kind of looked like this, then it went up here, then it came down here, and then it went like this. Now here's the problem. The derivative, the slope of the curve, if I zoom in here till it looks straight, the slope here should be negative. So I would expect my derivative graph to be scaled on the negative side of this vertical number line. It's not. Another problem, right here. The derivative should be 0. It's not. In here, the derivative should be, okay, that makes sense. So there's some parts of it that make sense, but there's other parts of it that just don't make sense. Here's the point. That's not it. That is not the derivative. Now, when you come back to class next week, I will fill in some of the details here. But here is the truth. This is no good. That is not how you take the derivative of a product of two functions. Even though it feels so good to just take the derivative of that first term, take the derivative of that second term, it doesn't work. I hope you can see that. Here's the reality. Now, as I said, I will get into the details, fill the gaps on this later, but for now, here's the question. If my function is x cubed times e to the x, what we just found out is you just can't take the derivative of this and get 3x squared, take the derivative of this, and it doesn't work. It doesn't fit our understanding of how derivatives work, but here's what does work. See that x cubed? Do not take the derivative. do not take the derivative. See that e to the x? Go ahead, take the derivative. The derivative of e to the x is e to the x. Plus, see that x cubed? Now take the derivative. See that e to the x? Don't take the derivative. In other words, don't, do, don't. We'll fill in the gaps here next week, but the idea is on a product. If you have a product of two functions like x cubed and e to the x, don't take the derivative, do take the derivative, plus do take the derivative, don't take the derivative. In general, it works like this. If you have a function that is the product of something times something, I'm just picking some letters here, u times v, then the derivative of that function, now what I mean by u times v is maybe u is like an x cubed and maybe v is like e to the x or any other functions that you can imagine. But what you do is you don't take the derivative. Then you do take the derivative. Then you do take the derivative. And then you don't take the derivative. And what we get here is what's called the product rule. So I challenge you now, take this version of the derivative and get back on your Desmos and graph x cubed times e to the x plus 3x squared times e to the x. Graph it and see, is the derivative function negative when it should be negative? Is the derivative of function 0 when it should be 0? Is the derivative of positive when it should be positive? Is it 0 when it should be 0? Is it? Check on Desmos and see if this actually makes more sense. All right, now, a little bit quicker format. I want to take you through another situation with derivatives that are important for us in this class, and that is this situation. Imagine you had a function that is, I don't know, like an x squared divided by e to the x. So instead of a product, x, whatever I had before, x cubed times e to the x, imagine a quotient x squared divided by e to the x. And again, we want to find the derivative. And so sometimes, again, people think, well, just take the derivative and just take the derivative, and trust me on this one, if you check this out, there's just no way that that's going to be true in terms of thinking about what derivatives really measure. And so we need a way to find the derivative of a quotient. Can you imagine this? Imagine a function that is the quotient of some function and another function. So like maybe this numerator is x squared and this denominator is e to the x. And we want to take the derivative. So I'm going to develop here for you how that might happen in general, and then we'll apply it over here. Here's how it would happen in general. In math, we often like to fall back on things that we know. Pretend with me, and if you need to, rewind the video, but pretend with me that you know how the product rule works. So multiply both sides of this function by h of x. So imagine you multiply f of x times h of x, and you multiply this fractional thing times h of x. You get this. Now the reason I do that is we have a product. We remember how, or rewind the video if you need to. We know how to take the derivative of a product. Don't take the derivative. Do take the derivative. Plus, do take the derivative. Don't take the derivative. Now you, I'm sure, learned in an algebra situation that if you do something to one side or an equal sign, do the same thing to the other side. So even now, if you took the derivative of the left side, you should take the derivative of the right side. So I took the derivative here with the product rule. Don't, do, don't. Take the derivative here. Now, track with me here for a minute. Here's the goal. I started with a function that happened to be the quotient of two other functions like this thing here. I want to find the derivative of that function. That is, I ultimately want to find f prime of x. Notice that f prime of x is right there. What we're going to do is just algebraically manipulate until we figure out what that f prime of x should be. Would y'all mind if I first subtracted this term from both sides? Like imagine subtracting from both sides. So what we'd be left with is again, just keeping our eye on the prize here, keeping our goal, we're trying to isolate this because I want to come over here and find the derivative of a function f of x that happens to be the quotient, and I'm now just building for any quotient, how would that thing play out? You got one more step to go. Divide by h of x. So if you divide by h of x, you will get that. So, to take the derivative of a quotient, here's what you do. You take the, you take the numerator, and you take its derivative. You take f of x itself. You multiply that by the derivative of g. You divide all that by h of x. I don't like that. I don't like that the derivative of x depends on f of x. And so I'm going to fix this up just a little bit. And I just realized I wrote h prime of x here, but when I brought it over here it became g prime. I'm going to make that fix. I feel better now. You probably saw that and were yelling at me. I'm going to fix this. I don't like that f of x is there, so we're going to make a quick little fix. F of x is equal to g of x over h of x. So this f of x is equal to g of x over h of x. Okay, now, to get the derivative of f of x, we're going to take the g of x, the numerator, take the derivative, minus, we're going to take g of x over h of x, multiply it by h prime, the derivative of the denominator, and divide all that by h of x, the denominator. Okay, still one more thing I don't really like. I don't really like having this fraction in the numerator. So, doing some good algebra here, we can fix that. We can take the numerator and multiply through by h of x, so that we cancel that out. But you just can't do that. You have to also multiply the denominator by h of x, so that if you notice here, we're multiplying by a form of 1, which is cool in terms of keeping equivalence. And so here's what we're going to have. This whole numerator gets multiplied by h of x, so I got to distribute it through. So I have to take h of x times g prime of x, subtract. Now when I distribute it in here, the h of x's will cancel out, and I'll just have h of x times h of x is h of x squared. And this is what we call the quotient rule. So it's a little bit more involved than do, don't do, like on the product rule. We have a little bit more to go, but I hope you can track. Let's actually apply it now. Notice that in this case, following the form, the numerator is g of x, the denominator is h of x. So in my case, g of x, the numerator is x squared. H of x, the denominator is e to the x. So let's take the derivative applying this quotient rule. Here's what it says. The derivative of f is h of x. H of x in my case is e to the x. Multiplied by g prime, multiplied by the derivative of x squared in my case, which would be 2x. Minus g of x. G of x is just that numerator, x squared. times h prime of x. That's the derivative of the denominator. Now the derivative of e to the x is just e to the x. And then all of that is over h of x squared. And in my case, h of x is just e to the x squared. Now this is the appropriate way to take the derivative of a quotient of two functions. And I hope you kind of get a sense of why it is. You might go on Desmos, graph this function, graph its derivative, and see, is the derivative positive when it should be positive? Is the derivative negative when it should be negative? Is the derivative 0 when it should be 0? It will be, I promise.